Okay, let's begin. So a couple announcements first. Today there's a dinner this evening at 5:30 in the dining hall hosted by the director of the IIS, and so all the participants are invited to that. So please participate in that. And I'm reminded to tell you to make sure to bring your name tags for that. Okay, in addition, there's a pool party scheduled for next week, but because of the weather, the director decided to graciously offer his pool also for tomorrow. So there'll be a pool party tomorrow from, I think it's 7 to 8, but we'll get you more information tomorrow. So those of you interested in either swimming or just hanging out at the pool, that's available tomorrow evening, and we'll say more about that tomorrow. Okay, so where we ended last time, we discussed the soft Higgs theorem for the coupling of, or for the, if you like, the emission of a real or virtual Higgs, or equivalently, the coupling of a Higgs in an effective theory for any process in the limit that the Higgs is very soft. And we used that to easily write the coupling of the Higgs to two fermions and to two massive spin 1 fields that gain a mass from the Higgs mechanism. So in the former case, we found that the Higgs couple is proportional to the fermion mass, and for the bosons, it coupled to the mass squared, and one could also use that to calculate the Higgs self-coupling to itself. Okay, so next I want to extend that to the coupling of a Higgs to two massless gauge bosons, massless spin 1 particles, that do not gain a mass from the Higgs mechanism. So in the standard model, that's the gluon and the photon. So using the Lagrangian interactions when we set all the fields to zero momentum like we did for the massive gauge fields and for the fermions, that won't work, because if we ask what the amplitude is for a massless photon, the two-point function at zero momentum transfer through the photon or the gluon, that vanishes because they're massless by definition. So there's no coupling at that order, but in a momentum expansion, there could in principle be a coupling at next order in momentum squared. So that would be a different operator. And so we can identify the operator and then ask the same question in the soft Higgs, using the soft Higgs theorem of what's the coupling. So the operator is already there in the Lagrangian. It's just the gauge kinetic term. Gauge kinetic terms for the photon and the gluon. And so remember, in the soft Higgs theorem, what we have to do is take a derivative of an amplitude. Here, so we've represented this amplitude in this operator in the low energy theory, say at a GeV for the coupling that we'll do later for the coupling of a Higgs to a nucleon. And the quantity that we're interested in, we want to know how, in this case, this coupling constant, the gauge coupling that sets the kinetic normalization for the gauge fields, how that changes when we make small changes in the Higgs expectation value. Now, at tree level, this is just, in the classical theory, this is just a number, and so there's no dependence at all. But in the quantum theory, the gauge coupling, because the theory violates scale invariance, although it's scale invariant aside from the Higgs mass term. The gauge part is scale invariant classically. It's not quantum mechanically. Scale invariance is broken explicitly. And so the gauge coupling depends on the scale. And we can write that, the variation of the gauge coupling in the effective Lagrangian with scale. That's quantified through the beta function. So the beta function for 1 over, so what we're interested in here is the beta function for 1 over g squared. And so at one loop, it's given by some number. So the 8 pi squared over g, 8 pi squared in the denominator counts a loop factor. B is called the one loop beta function coefficient. And then there would be higher order terms, so beyond one loop. And in SUN, B is NC, so it's 11/3 NC. With positive sign, that corresponds to asymptotic freedom. And then with opposite sign for matter fields, so for Weyl fermions in the fundamental or anti-fundamental representation, and same thing for complex bosons. Okay, so this equation, this beta function for 1 over g squared is extremely easy to integrate at one loop because there's no g squared dependence here. That's one reason it's nice to write the beta function for 1 over g squared. No g squared appears. And so it's easy to write this, given this beta function, this number in any theory, we can write down the scale dependence of the gauge coupling. So we can relate the gauge coupling at 2 different scales in our effective theory by integrating this beta function. So the beta function just contains this information. So for example, if we did a loop calculation with some matter, light matter, that can run in that loop in the low energy theory, then if we calculated this 2-point function at one loop, it would give us this log, and this beta function is just a way to capture what the coefficient of the log is. Okay. So now let's come to the effects. So now what about our question here of what the variation of the gauge coupling in the low energy theory is if we vary the Higgs expectation value? So again, we're going to use the soft Higgs theorem. So what we're interested in is essentially this diagram where there's a Higgs, say 2 gluons, at some very low energy scale, maybe of order of GeV, coming from the effects. So here we can see graphically or diagrammatically what the effects come from. The effects will come from heavy fields that can contribute to the 2-point function for the gluons, but that also couple to the Higgs field. Okay. So let's just focus on the most important one, the top quark, because it has, it's most important because it couples most strongly to the Higgs. So let's start with that one. But now we can see what the effect is of the running gauge coupling in the full theory, in the effective theory below the top mass scale and above the top mass scale. So let me just draw the solution of this equation graphically. So here's 1 over g squared as a function of log mu. And so there's some scale where things change. So in a high energy theory, all the light quarks and the top quark can run in the loop. And the beta function has some value. And at one loop, it's just a straight line with slope given by the one loop beta function coefficient. In a low energy theory without the top, likewise, the gauge coupling runs in a similar way, changes with scale in the effective theory. But now the beta function coefficient is different because the top is heavy. It's not part of the low energy theory. And so it has a different coefficient for the one loop beta function. So the slope is different. So if we want to ask a question down here at some low scale, so this is the low energy theory and the high energy theory, and there's something I'll gloss over here. I drew these as if it just comes to this point, and then I connected the straight lines, and you could ask, well, in general that's true. If you're at a scale, say you put momentum through here at energies for p squared much, much greater or less than the top mass, then it's true, but in general, there's some finite correction that comes in addition to logarithms. But it turns out if you work in any minimal subtraction scheme, those modified minimal subtraction, and that choice is actually made so that precisely this calculation of matching the running of gauge couplings in a modified minimal subtraction scheme is one such that the finite terms, the finite corrections here that would come from integrating out in the top, in other words, just a number without a logarithm, those vanish. Okay? So I haven't cheated you actually. Well, there's some scheme in which I haven't cheated you, and it's any modified minimal subtraction scheme. Okay? So this is perfectly adequate. We haven't made any approximations beyond one loop. And now we can answer we can answer it graphically, and then we'll write the equation. So now we want to know, how does the low energy gauge coupling change as we change the electroweak scale? But if we change the electroweak scale, holding everything else, all the normalizable couplings in the theory constant. So again, remember, that's like there's a wave in the magnitude of the expectation value of the Higgs field, or what would be the expectation value in the global limit, locally. And so if we change that, the top mass locally changes if we keep the top Yukawa coupling fixed. So the question we want to answer is, the change in the weak scale, that's proportional to the change in the top mass. So you see, if we change locally, if we change infinitesimally the top mass in some region, then the matching scale here changes, and that's reflected in the change in the gauge coupling at low energies. So this heavy threshold depends on the electroweak scale, and that'll be reflected in the dependence of the coefficient of the kinetic term for the gauge kinetic terms. Okay, so let's write coming from this interaction here, the M dependence, let's write the M dependent, M top dependent contribution to the gauge kinetic term. Well, it's easy to just read off this equation. From this equation, it is, I'll even get the sign right. It is minus delta B, where delta B is the B changing going through the threshold, over 32 pi squared, log of the mass of the particle, so I'll just write on top, times the gauge kinetic function. And so now we can take our derivative. Well, we can take so I just rewrote this, and so now this is the whole term here. So now we can just take the derivative and get our answer. So the derivative with respect to v of log of m over mu is 1 over m dm dv. And as we said last time, for a field that gets all its mass from electroweak symmetry breaking, then the rate of change of m with respect to v is just m over v itself, because it vanishes when v goes to 0. So this is just 1 over v. So let's write it here in the next board. Oh, maybe I'll write it over here. So that means when we plug in, one last piece of information, then the delta B for the top quark is minus 2/3 per single flavor. So the effect of from the heavy top threshold in the low energy theory to coupling to the Higgs, if the Higgs were very light, this would be well, as we'll see in a second, it's light enough for this to be a pretty good calculation. So it's 1 over 48 pi squared h over v times the gauge kinetic function. So that's for the gluons. Now, a couple comments. This was one loop, but in this using the soft Higgs theorem, we could get the answer to any number of loops we like, as long as somebody has calculated the beta function. We could just plug in here the higher corrections and put those expressions in, and we would get the corrections. So we can do as many loops as anybody's calculated for the gauge beta function, again in the soft Higgs limit. Next comment, when is this a good approximation? Well, it should be a good approximation. So let's imagine we have a real Higgs decaying to 2 gluons. So when is this soft Higgs approximation good? Well, it's good when the effective field theory description should be good, and that even tells us at what order we expect the correction. So that's good when the thing we're integrating, effective field theory is good when the things we integrate out are heavy compared to the scales we're interested in. And so for this real case of a real Higgs decay, then the p squared through the Higgs is equal to m Higgs squared. So that should be much less than the top mass squared. In fact, in effective field theory description, we could even calculate corrections at next order in a momentum expansion. So we could calculate the p Higgs squared corrections. Those would correspond to operators that look like this with 2 derivatives acting on the Higgs field with some other coefficient here. Okay. Now from those we can't get a nice simple answer from the soft Higgs theorem, but okay, that's what we know parametrically what they look like and at what order they would appear. Another comment is, notice that the top mass dropped out. There's no dependence, again, in this limit here, on the coefficient of this operator. So in other words, as long as the particle that was being integrated out was heavy, it didn't matter how heavy it was. So in our calculation, that just comes from the fact that the one-loop beta function only depends on the log of the mass. So there's no, reference to the overall scale. You could also just do, well, we could, if somebody wants to see it in the discussion section this afternoon, I can do it. Here, if we did an analysis of this loop diagram, we would see that in the high energy theory, it's infrared, although there's a coupling here that goes like m top, it's infrared divergent, and that infrared divergence in the high energy theory is cut off by the mass of the particle here, which is m top, so there's an m top in the denominator. But in this calculation we did, we just see that from the logarithm right away. And finally, so there was a question yesterday about this. If we calculate this full dependence here of the next order operator, so that's some power for a physical Higgs decaying to the top, sorry, to 2 gluons through a top loop, then the calculation we did, so there's some form factor here, F, and the next order correction is, if I did it correctly, is this, and here's the m Higgs squared over m top squared. Okay, so for the physical values of the Higgs and top mass, the coefficient's not small, but this correction's small. So this actually is a pretty good approximation numerically, actually, to the real Higgs decayed at 2 gluons. Okay. So now, I want to talk about Higgs boson decays. And before I do that, could I just request that, I think there is a problem with the cooling in the room. Are people, it seems it's very muggy and stuffy up here. Here too. And there too. Could we maybe try to get the air conditioning turned on? I think it's actually not on. Okay, so now let's talk about Higgs boson decays. And then the rest of the lecture, I'll try to discuss things that will make some context for the talk of Chris Tully on some of the things that are going to be measured about Higgs bosons that are being measured now and that will be in the future. Now the Higgs clearly, well, at least at tree level, it couples to the things most strongly that have the largest mass. So as far as a Higgs boson decay, it'll decay, at least for two-body decays, to any two-body state that's open, and the heavier the particle, the standard model particle, the stronger the decay. So it'll like to decay to heavier things more than lighter things. So let's look at for a Higgs mass of the observed mass of 125. Let's just look at the two-body decays. So the two-body decays that are open are bottom, charm, tau, so forth. So in order. So among these, the bottom quark is the heaviest. Now the bottom quark mass. Let me just say one other comment here about these couplings. And we can see it in the soft Higgs theorem, these couplings here. Well, it's the same as Lagrangian coupling. So these couplings that we talked about from the soft Higgs theorem that are proportional to the masses, those are the masses, well, that's at zero momentum for the Higgs. But now if we want to talk about this at finite momentum, that's evaluated at a different point. But the right answer for that is to calculate quantum corrections that tell you the difference between the momentum, this amplitude at zero momentum here, and for p squared equals the physical m Higgs squared for an on-shell Higgs. But let's focus on the B quark and talk about quantum corrections from QCD. So those are numerically the largest. In the low energy theory, below the electroweak scale, there are corrections from QCD and electromagnetism at one loop. So the QCD corrections are just one loop corrections like that, plus vertex plus wave function corrections. But these corrections are exactly the same as the mass operator. Okay? So the coupling of the Higgs field here, when we say that it's the mass over the VEV, if we want to include the integration for integrating the leading contributions for the quantum corrections, what we should do is, since the running of this operator and the mass operator are the same, let's neglect the fact that let's just neglect the W and Z interactions for the moment. Then the mass scale, what we should do is use the running value of the mass. The mass is a parameter in the low energy theory, so all the parameters run under changes of scale. So that should be evaluated at a scale that's something like the Higgs mass. Okay? So here when we plug in these numbers, and it makes a big difference for the light quarks. The bottom quark mass at the bottom quark scale, or the pole mass, is about 4.5 GeV. But if you take that and run it up to the Higgs scale, using these QCD corrections, it's about 2.5 GeV. It changes a lot. Because the strong interactions are getting relatively strong, and it has, at low energies, and it has a long way to go. In any case, the relevant B quark mass is about 2.5 GeV. And so the value of the coupling here, for this thing that can decay to two-body, that it can decay to most strongly, is about 10 to the minus 2. So it's quite a small coupling. So the thing that the Higgs decays to dominantly, it decays to through a pretty tiny coupling. And therefore the width, the decay width, or the decay rate is very small. So the decay rate of Higgs to BB is, well, here, let's just estimate it parametrically. So there's a factor of 3 for 3 colors. There's a factor of the strength of the interaction, which is MB over the VEV, and we have to square that in the rate. And since the B is so much lighter than the Higgs, we'll neglect any phase space suppression, and that's it. And so to get the right units here, this has to have an M Higgs. That sets the scale for the phase space. And for two-body decay, the figure of merit is 8 pi, generally in the phase space. So up to a factor of, 2, it might even be exactly the right answer, I don't know. Up to a factor of 2 or so, this is the decay width. What am I doing? That's MB. And numerically, this is very small. It's 2.5 MeV. Let's see if I remembered it right. Yes, MeV. And as we'll see, this does dominate the decay modes of the Higgs. And so this is a very, very narrow resonance at this mass. Okay? If the Higgs had been heavier, so it could have decayed to two massive gauge bosons, 2 Ws or 2 Zs, then as we learned in the last lecture, the coupling of Ws or Zs at high momentum, so if the Higgs was very heavy, it shoots off very high momentum Ws or Zs, but the intrinsic strength of that coupling grows because they're effectively like Goldstone bosons that have derivative couplings. And so the decay width of if the Higgs had been very heavy, it could have gotten very wide. In fact, if you just use a tree-level calculation, from a similar calculation we did last time, you find that the width becomes of order of the mass when the Higgs is of order of TeV. Okay? So it's not even a well-defined resonance at some point. But way down here at 125, where it's so weak, it's an incredibly narrow resonance. This, by the way, is far, far smaller than we'll ever access at the LHC or even the ILC. People sometimes talk about muon colliders, where you would make incredibly narrow in energy beams of muons, positive and negative muons, and collide them, and sit on the Higgs resonance through the muon interaction. And there they thought, I don't know why, but well, I do know why, but let's not go into it. You might be able to get very narrow beams and then actually trace out they could be at the order, the beam width could be at the order of an MeV, and then you'd actually see the finite width of the Higgs. It would be like sweeping out the width of the Z at LEP. In any case, that's for another century, I think. That's for your grandchildren, students or something. Now there's another important decay. So this was two-body decays. They're also possible, well, like three-body, four-body, any decays that are open kinematically. So let's look. So there is an important three-body, two important three-body decays that are open. And that is where the Higgs, it can't decay at 125. It's not heavy enough to decay to two W's, but it can decay to a W and an off-shell W. That then turns into a lepton and neutrino, for example, in the final state. So now let's compare. So this is three-body, but the couplings are much bigger here. So the coupling of the Higgs to the W's is bigger, and this is a gauge coupling. So let's estimate the ratio of the rates here for the decay widths for H to WW star. Divided by the decay rate for the Higgs to 2Bs. Okay, so first off, there's a factor of V in the denominator for both of these couplings, so we don't need that in the ratio. Here, well, there's a G here that comes, so it gets squared because it's in the G's in the amplitude. This coupling goes, remember it went like the W mass squared, so this is the W mass to the fourth in the rate. In the denominator, there's an MB squared. And finally, to make up the units here, there has to be an M Higgs. Squared, yes. Okay. And in addition, this is three-body versus two-body, and every time you add a body, parametrically, that's a factor of 1 over 16 pi squared. Okay, so when you plug all those numbers in, this is of order 1. And so even though this is a three-body decay, since it doesn't have any suppressed couplings, it has about the same branching ratio, decay width, partial decay width as the Higgs to BB. Okay. So now let me make a table now, numerically, of all the important, or many of the important branching ratios for the Higgs. So for BB, so this is just the partial width adding up all the total widths. Again, this is at 125. So the BB is about 60%. WW star is about 20%. Glue through the operator that we just calculated. It's about 8%. Tau, so this is all in descending order. Branching ratio is 6%. CC is 3%. ZZ star is 2%. Z bosons couple to everything more weakly than W bosons, and they're a little bit heavier. So the phase space suppression starts to really kick in for those, so that accounts for this factor of 10 between ZZ and WW. Gamma, an experimentally very important one, is very rare. That's this one-loop process that we just calculated. That's 2 times 10 to the minus 3. And finally, another one that will become important eventually and will be seen is dimuons. That's 2 times 10 to the minus 4. And the total width of the Higgs is 4.1 MeV. So there's a couple features here that are important to notice. First are that some of the decay modes give resonant final states, like the diphoton, the dimuon, and in particular the case where ZZ goes to 4 leptons, that has a very small branching ratio, but it's resonant. So that means that all of the energy in the decay goes into visible particles that can be reconstructed in a detector, so you can sum all their 4 vectors up and find the invariant mass. So these are the modes where the mass of the Higgs can be directly reconstructed. Now, interestingly, these are all very rare decay modes. So the decay modes that are nicest kinematically are very rare. The ones with largest branching ratio, that has the largest branching ratio, has very large background. So this by itself inclusively is not of much use. And there are also non-resonant modes like WW and some of the ZZ and the tau-tau. Well, tau-tau is also resonant. Sorry, that's what I left out. But the taus are not easy to construct. The BB is resonant, and they're also not easy to construct with large backgrounds. So there's a wide range of different types of interactions, or different types of branching ratios, and lots of possibilities for the experimentalists. Next, let me mention the production modes. So that's how the Higgs decays at 125. Let's look at the production modes. So there are 4 main types of production modes. So one is from glue-glue fusion. We've already discussed through the top. So that gives a resonant final state. The next is, so this is glue-glue. The next is vector boson fusion. So that comes from a process where there are quarks or antiquarks in the initial state that emit either W's or Z's that then fuse together to make a Higgs. Now this is 3-body. And remember, adding bodies always suppresses the phase space. There's always a phase space suppression for adding extra bodies. But here, the W is so light compared to the energy scale of the beams that it's almost a parton. In fact, there's something called the effective W approximation, where you just treat W and Z bosons as if they're partons and do the same formalism that you heard about this morning for splittings and so forth. And that's actually not such a bad approximation. So it's 3-body, but it's really almost resonant. Another is VH associated production. So that's when the QQ bar interact through a W or Z and emit a Higgs. And the final is produced in association with TTH. So these are the dominant modes, and so that's gluon, predominantly gluon fusion that gives 2 tops. And then one of the tops, Bremsstrahlens irradiates a Higgs boson. So this is truly 3-body. These are all heavy 3 bodies, so that suppresses this. This is 2-body. The gluon gets a big enhancement. The glue first because it's resonant, and the gluon PDFs, as you heard this morning, are the largest of all the PDFs. This all happens at pretty small x, right? Because the Higgs is quite light compared to the beam energy. So this dominates. These other modes give the opportunity to make tags, make special categories that try to look for the other things produced in association with the Higgs. So in this case of the vector boson fusion, what one can look for is these extra quarks that go along, spit off a W, and then go out at a small angle. So what one looks for are 2 jets, one in the forward direction and one in the backward direction. Of course, that can happen just from radiation too, but at least this production process by definition has that. So that increases the signal to background. Here one looks for the associated W or Z with the Higgs, and these can have leptonic decay modes that helps get the background down significantly. Excuse me, here one can look for the tops, but there's enormous production of just top pairs anyway, and so the cross section's low. So this is quite a difficult channel to see. Let me just write down the cross sections for these, and I'll just write them at 8 TeV for 125 GeV, and I'll write them in femtobarns. They're typically a factor of more than 2 bigger at 14 TeV. So this is 19,000 femtobarns. This is 16,000, 1,600. This is VH is 700 plus 400. That's for W and Z. And TTH is 130 femtobarns. And I remind you that there's 20 inverse femtobarns per experiment. So if you add all this up, there's almost 1 million Higgs bosons have been produced. But of course, most of them come from glue-glue fusion, and most of them decay to BB bar, which there's enormous background for. So most of them are not even recorded, actually. Okay. Now, what experimentally is done is to look in various channels that I'll list as IF. See, there's a lot of possibilities. So by tagging this initial states and looking for the various final states, experimentalists, there's a whole matrix that they can look for of different channels that correspond to trying to isolate a given production mode, so I, and a given decay mode. And just as one example, at the discovery level, or just to, so all these, some channels are good, some are very difficult, but as you'll hear in the experimental talks, almost every combination, let's see, I did a check here. At the moment, so at the discovery level, there were 3 of these channels that were relevant. So that was the inclusive diphoton. And let me just write this down. So inclusive diphoton. So there, the signal to background is much less than 1, but it's still big enough to see. And since it's resonant, one looks for a small bump on top of a giant continuum background. There's VBF, gamma, gamma. There, the signal to background, adding these extra tag jets gets it down to about 1, but the total signal is very small. And the inclusive ZZ, there, the signal to background is much bigger than 1. 4 leptons are very precious things. Basically, the first approximation, the dominant background are just 2 real Z bosons, or a Z and an off-shell Z boson. And so finding 4 leptons all at the same mass is very good. So the signal to background is much bigger than 1 in this channel. So which channels are most important depend on how much integrated luminosity there is. And you'll hear more about these in the experimental talks. Now, nature's been very kind to put the Higgs right at 125, because if it put it at some very large mass, only a couple of these channels might have been relevant. For example, the WW and ZZ, and that would have been it. But putting it there, many of these channels are observable. So now I did a count, and there's more than 10 channels that are that are seen already. That are not seen at a discovery level, but that are used in FITs and people are actively working on. And my estimate was that there'll be, of all these possibilities, in the end, by the end of the LHC program, there'll be more than 20 different channels that the Higgs will be tagged in production and decay. So that's a really interesting system for the experimentalist, and there'll be lots of nice measurements of just the rate measurement for all these production. They'll all be of the form of the cross rate measurements in these various channels. And so let me just contrast that with the top quark, where, okay, the top quark, there is one channel. It only decays in one way that's ever been seen. So there'll be lots of information to extract from all these. Yeah, there's a question. Okay, so these resonant ones, either like the gamma gamma or the mu mu. So what you do there is you look at so you prepare you prepare a sample that has two opposite sign muons or two photons, and there's a giant continuum background. And so you're looking for a relatively pathetic little signal on top of that. So you're looking for a tiny little bump. And I'm sure you've all seen the discovery plots of the diphoton. So for the mu mu, the background, it's called Drell-Yan background. It's a process like this where quark-antiquark can make a dimuon pair. And that's not particularly small. It's electromagnetic interaction, but there's nothing else suppressing it. Say again? Yeah, so, okay, so there's also so in that case, yeah, thank you. So let's just draw this here. So this is gamma gamma. And in the Z case, of course, there's this giant, enormous Z peak. And, well, we know, so first off, we should and are looking for little bumps, all along the spectrum. But now out here at 125, it's out in the tail, away from the Z, but there'll be a little bump there eventually in Higgs to dimuon. Okay. Yeah. By the way, the first approximation, if you just get a dimuon data set from the LHC and plot the invariant mass, it looks roughly like this. I mean, the first approximation, it's all Z. The Z is just a horrible thing. Well, okay, so that's part of I don't want to go too much into we could maybe do that. I'm happy to talk about all these experimental little, why things work, why they don't, what do you do. But remember that the Higgs is extremely narrow. So the width of this is all determined by experimental resolution. And so a lot of work went into squeezing the resolution as much as could possibly be, because the more you squeeze it, then it sticks up more from this continuum background. So it's a question of what the resolution is. That's basically, for muons, that's basically a fixed thing. There can always be incremental improvements. And it'll be a while before there'll be an observation in a dimuon, but if it's there with standard model strength, it'll come eventually. Maybe in the next run. By the end of the next run, it'll be observed in that mode. Okay, so now for these rate measurements. So I just want to talk about the interpretation, some different interpretations of these rate measurements and what they're good for from the theoretical side. So before I do that, I just want to draw a picture. So the collaborations, what they do is they simulate each of these processes. So they have they have a VBF tag channel, and they simulate every possible production mode in that channel. So for example, some of the actually quite a bit of the glue-glue fusion production shows up in the VBF channel, because this can just radiate two jets in the forward and backward direction. So, but they model all that so they know what the channel migration is. And then in every final state that they look for, like diphotons, di-Z, di-tau, and so forth. Then from that, they do a fit to the strength in each channel, which then gets converted, knowing the acceptances, into a cross-section times branching ratio. And from that, using the theory, what they do is they let the couplings of the Higgs bosons to all the standard model particles float, and then they find where all this constrained data wants to have the best fit, and then also taking careful account of all the uncertainties, the systematic uncertainties, all through the chain. It's a very complicated process. You'll see lots of results of this later in the school. They can get bounds on how big the couplings are, what their allowed values are relative to the standard model expectations that we talked about just now. So one way to present that is, let's plot a log of the mass of the particle versus log of the coupling. So I just well, here I'll call it Higgs X and this particle X. Okay. Now, from our previous discussion, and these are the tree level couplings. So the important ones here for all these measurements so far are the top, because that comes in the glue-glue loop, the bottom, because that controls the total decay width and therefore all the relative branching ratios. The couplings to tals. There's just barely a tal signal showing up now in the searches. The couplings to the W and the Z. Okay, so those are the important couplings. So that is 1, 2, 3. Yeah, so I said them all. That's 5. Now, we just showed from this soft Higgs theorem that the couplings to fermions go like mass, and the couplings to the heavy bosons go like mass squared. So there's a prediction for where the coupling should land here. So there's a line with slope 1 for the fermions, and there's a line with slope 2 for the bosons. Well, we know what the masses are already, but the prediction is that the fermions will land on this line and the bosons will land on that line. And, well, you can look on the CMS website to see the latest version of this. So for the top, there's some uncertainty. And again, I won't even say how big these are. I just want to draw this schematically. So this is the top, bottom, ZW, and tau. And everything lands right where it should, and just this nice pattern of masses for the fermions and mass squareds for the bosons with just the right values. Now, the uncertainties in a lot of these are large, or 50%, 100%, almost 100%. But those will come down. So I think this is a nice graphical way to show that the couplings are just landing exactly where they should, the first approximation, if it's a Higgs boson. So it's a Higgs boson, okay? I mean, it's interesting to make these straw men, well, what if it's a spin 2 this or that? What if it's a dilaton? What if it's not the Higgs? But once you see this picture, you can come up and see it afterwards if you want to look at it. It's the Higgs, okay? There's no question, it's the Higgs, the first approximation. All right, so that's the first comment I wanted to make. Now, at a more quantitative level, well, so part of the program, of studying the Higgs boson, will just to be making these rate measurements more and more refined rate measurements, fitting to a hypothesis that the Higgs is decaying to just standard model particles, and then let's try to measure their couplings as well as can. Okay, so it's already starting to pay off. And I just wanted to discuss, since that's going to be a major part of the experimental program, it's a very rich experimental program, as I said, because there's all these over 20 channels eventually where these measurements will be made. So there'll be tons of information. And any deviations from the expectations here, once the error bars start to squeeze down, would indicate new physics. Because remember, the couplings of the Higgs field now, everything in the renormalizable linear sigma model, standard model, all the couplings are now fixed since we have the Higgs mass. Okay? So we can calculate everything. So there's no question about where these couplings in that theory land. And if we find that something eventually gets pulled out from what the prediction is, that means that there's some, that will be a clear indication, in as much as it will be a clear measurement, that will be a clear indication that this linear sigma model Higgs sector is not the right one. Something else is there. So I just wanted to make a couple comments about interpretations. Now, one way to parameterize any measurements like this is when you have a theory that works very well, like the standard model, and again, the first approximation, now it's working well in the Higgs sector, is to start with the renormalizable theory that makes predictions, and then parameterize any deviations in an effective field theory framework where you now start to write general operators that are non-normalizable of higher dimension, that are more irrelevant. And then add those into these fits in principle and see what the bounds are on those extra operators. So we had a discussion during the discussion section yesterday, we were discussing the fact that there have been precision electroweak measurements, I'll write the operators here in a second, that tell us that the renormalizable standard model works very well. So we don't see any structure in any of the interactions. So we use these effective operators to parameterize structure in the interactions. Okay, so this program of parameterizing deviations from the normalizable standard model is now going to take off and it's been a very interesting subject. It's going to be even much more interesting now that we have all these rate measurements. It really just opens up, well, it opens up the complexity enormously, but there's a lot of opportunities, therefore, to maybe see deviations too. So I just wanted to tell you a little bit about that. So the leading corrections, if we parameterize it in this way, in this effective operator language. See, by the way, this is a good way to parameterize deviations if you don't want to commit to any specific ultraviolet completion of the theory. And because the most general ultraviolet completion will show up somewhere in the most general effective theory if it's at a slightly heavier mass scale. And since things are working so well, it's a good way to do it. You know, you can also commit to a given UV completion, but well, this is a nice systematic way to do it. Now, so the leading corrections beyond the marginal operators in the Higgs sector that involve the Higgs come at dimension 6. Yesterday I wrote the only class of dimension 5 operators, so those are the leading ones. Those are the neutrino mass operators. And we have good experimental information about those now, but beyond that then they're dimension 6. And there are 50 plus operators. So that's a lot. And so it's useful to make some simplifying assumptions. And so that was done a long time ago. So there's two simplifying assumptions that collapse this 50 down to just two operators. And they are, first, that one uses Higgs VEVs only. And the second is that the operators are called oblique, which means that they include interactions between the Higgs and the gauge sector only, and no fermions. So, okay, we could make that choice for simplicity. There's some classes of physics that we think we could have thought existed at the electroweak scale, just above the electroweak scale, that do satisfy that. The main motivation would be if there's any other structure in the Higgs sector, the things it couples to most strongly, well, aside from the top, are the gauge bosons. And if we had an effective theory where we integrated out the top, then it would be in these operators. Okay. So let me write I think I'll write.
Excuse me, what do you mean by the Higgs VEV?
Okay, so that means in the operators, so these 50 plus operators, they involve Higgs fields, many of them, okay? And so pre-2012, the only relevance for any of those operators is you take the Higgs field and replace it by its VEV, experimentally, right? Okay. But now we actually have excitations of the Higgs field, and so more of them will become relevant. In fact, in principle, they all become relevant. Okay. And I'll show you an example here in just a second. I'll write it here on this blackboard. So let me show you the two that are relevant, an example of two more that are irrelevant, and tell you why just the Higgs VEVs don't do much for some of them. So the first one is, I'll write coefficients here. D mu H dagger TAH. H dagger TAH. Yeah, by the way, I can absolutely verify that the air conditioning is not working. I think it's slightly hotter up here than it is down there. So let me write these two operators and then tell you about them. So W is the SU2 field strength, B is the hypercharge field strength. let me write the other two and then I'll explain them. So these coefficients are just to pull out factors of the gauge coupling if it comes with the gauge field strength. And this is just the coefficient to give it an arbitrary coefficient, and m is to set the mass scale. So it's some arbitrary scale because it's dimension 6. And another one. Where's prime? Let's see, this is 1, 1, 2, 2. Okay, so same thing, the gauge kinetic term times h dagger h for the hypercharge and SU2 gauge fields. Okay? So these are 4 of the 50-odd operators. Now the first two, let's say what the first two are. Well, first off, let's start down here and explain this fact of what, okay, with VEVs, why weren't they interesting pre-2012? Well, here, if we replace these things with expectation values, then all that does is that just modifies the magnitude of the gauge kinetic term for in this case, the hypercharge. But the magnitude of the coefficient is just 1 over the gauge coupling squared. But you didn't know what the gauge coupling squared was anyway. So it shifted the gauge coupling from some number you didn't know to another number. So there's no more information, okay? So when we only had information about the Higgs, when you had to just put Higgs expectation values in here, lots of operators like this just didn't have any impact on any experimental measurement, okay? These first two are different, though, with Higgs expectation values. The first one here, we can see by eye what the effect is. Remember yesterday I said that if there were a triplet Higgs field that got even a small expectation value, that would modify the relation between the W and the Z mass, because that depended on the representation of whatever appears in this global limit as the order parameter in the vacuum. But here you can see this looks like a kinetic term for the things I wrote in parentheses, but these things I wrote in parentheses, this is a composite field made out of the 2 actual Higgses that are doublets, but it's a 2 times 2 in the triplet combination. Okay? So this is like a composite triplet field. But now it appears in this kinetic term, so when we write out the heavy gauge boson mass matrix, it'll have a contribution in it just like as if there had been a triplet. It's from this composite triplet, okay? And so that's bounded very well. This scale is bounded at a few TeV. Okay? This operator is interesting. So it's interesting, again, since the W and Z masses are measured so well, that's bounded well. This one's also bounded well, and the reason is because when you put Higgs expectation values here, it's a type of term that doesn't exist in the renormalizable theory. It mixes, it's gauge kinetic mixing between the SU2 gauge field and the hypercharge gauge field. But without the Higgses, that's forbidden by gauge invariance. Right? There's no term like that there at tree level. So that gauge kinetic mixing also modifies any observable that involves the Z boson and the photon. Okay? And so that modifies details of the masses and so forth too, in different ways than this, but so this is also measured very well. So these two were written down by a number of people. They were called by Peskin and Takeuchi. This one was called the T operator, and this one was called the S operator. There was another dimension 8 operator that they called the U operator. We like to call things, if there are 3 of them, we like to call them ST and U. And I guess we think everybody will forget that that's been used multiple times in various contexts. Anyhow, that's all right. Anyhow, the name stuck. So the precision. So now again, the renormalizable standard model makes predictions for relations among observables. And so one can do a compilation of all the precision measurements I've made, like the W mass, the Z mass, the Z width, forward-backward asymmetries, because the weak interactions are not parity symmetric, and so forth. Paul Langacker here is one of the world's experts on that. And one can check whether those relations work first in a normalizable standard model, and then add as a extra free parameter these two operators. And I'm just telling you there's two without proof, but those are the only two that are relevant with these assumptions. And then from that you can get bounds on the coefficients of these operators. And so Peskin and Takeuchi normalized, so they used S and T for the coefficients. They used some normalization that I think must have been motivated by Technicolor or something. So it's kind of outdated, but the normalization is stuck and people are sort of calibrated in the how big these are. So in terms of this S parameter, S is measured to be consistent with 0 and at 1 sigma with an uncertainty. So it's a dimensionless parameter. Here we pulled out the V squared of about 0.1. And so that corresponds to a scale here for that operator that's bigger at the 1 sigma level of 3.9 TeV. So that just gives you an idea how what the scale is for these things. Now, just as an aside, it was also mentioned yesterday that previous to discovering the Higgs, there was good indirect evidence that the Higgs actually was light, that it was in the 1 to 200 GeV mass range. And that came from essentially calculating a loop effect to this operator S in the standard model. That's one way to think about it from the following diagram. I won't take time to estimate the magnitude of the diagram. Again, we could do that in the discussion section. So at one loop in the standard model, there's a contribution to this S operator. And it depends, with a Higgs boson in it, so it depends on the Higgs mass. Okay? And so that goes in to that's part of the standard model part of the fit. And if one treated the Higgs mass as a free parameter, setting the S and T to 0, then that gave an indication. So that's a fit to a hypothesis that it's just a renormalizable standard model with this one last parameter that we haven't measured, M Higgs. And that indicated that the Higgs was well, it ended up right, consistent with those indirect indications. Okay, so now things have now, so this is all pre-2012. So now post-2012, things are now changed. Because now many of these other operators are in this effective field theory analysis can be probed. They're not just irrelevant rescalings of couplings like the last two there. And again, so the Precision Electroweak program can be expanded to include all these fantastic measurements coming from these things I just erased here for the Higgs. And one could go off and do this now it's not 2 dimensions anymore, it's 50 plus dimensions, and see where the best fit is and what the bounds and all the operators are. Okay, rather than do that, let's ask the following question, which is a more interesting question. What will be the best measured of all these different channels in any combination? What will be the best measured, say now and in the future? So the best combination of Higgs rate measurements. Okay, well, the best ones will be the ones where you can identify that you have a Higgs signal most easily and directly and convincingly. And those are the resonant channels. So the decays, and the ones that have been seen so far are the diphoton and the di-Z. They're there at the discovery level. Okay. So those are the best rate measurements. By the way, they're good because one reason they're good is experimentally, you can use nature to do the background calculation. Since you have a resonance over some background, you can just go in the side bands and nature does the calculation for how big the background is. And then you can extrapolate into the signal region, and so you know how big the background is here, and so you can make a signal measurement. So you don't have to model all the background a priori. Okay? That's one experimental advantage of the resonant modes. So the systematics are better in those modes. Now you can do even a little bit better by taking ratios of observables because certain systematic uncertainties drop out. And there's an important one that drops out if you take the ratio of these two best resonant modes, the gamma-gamma to ZZ. Just as an inclusive measurement. So most of the cross-section, as was over here, comes from the glue-glue, but the glue-glue suffers relatively large theoretical uncertainties. But if we take these ratios, those theoretical uncertainties in the PDFs and the ability to calculate at 2 and 3 or more loops, the process drop out to a very high degree. So this will be, for all these reasons, of all the rate measurements, the best measured combination of any of the rate measurements, okay, with the lowest uncertainties, systematic uncertainties. In fact, for a very, very long time, the dominant uncertainty in this ratio will come from the fact that there just aren't that many ZZ to 4 lepton events, so it'll be statistical. But eventually, you know, when there's multiple inverse attobarns, even that'll be overcome. So this is something that can be measured maybe down at the percent level, eventually, few percent level. Yes, go ahead. I'm sorry, say again? So one of the things is that you have to, so that is one uncertainty, so the experimenters have to quantify what the acceptance and efficiency is. But they're very good at that. So not everything drops out, it's 2 different channels, but many of the things do. Okay. So it's not completely free lunch. I mean, a completely free lunch would be, for example, if there were 2 diphoton resonances right near each other, or 2 di-Z resonances, that would be even better. Then almost everything would drop out. Yeah, so you measure the channels, but when you take the ratio, again, so for example, although it's not that important, there's uncertainties just from the total integrated luminosity. That's not known. That drops out. And again, the theoretical uncertainty for what the production cross-section is from glue-glue, that largely drops out. There's remnants, but we could discuss more in the discussion section. Okay, so I think without belaboring all the details, what I'll do is just draw the picture for what the impact will be from this measurement. So here we have S. So now I'm going to generalize Peskin's notation. I'll call it S12 because it came from this mixing hypercharge. And let's see if I draw a box here. And so if this is, the range here is about minus 0.6 to 0.6. You can come look at an actual plot here I have in my hand. I'll just draw a picture of it. And so again, pre-2012, there was some uncertainty here of about 0.1. But now we have a measurement of this from the Higgs. And I'll plot another linear combination here. This other one, S11 plus S22, that was irrelevant before. It's not irrelevant now. Because there's some linear combination, you see, of these 3 operators here contribute to the Higgs to diphoton ratio, or the Higgs to diphoton. Okay? And since the Higgs to diphoton is a loop process, it is most sensitive to any deviations. So if you assume that all the it's an assumption, but assume all the operators are uniformly small, then the leading effect of any of the operators, it turns out, to this ratio are just these 3 operators out of the 50. Okay? Without any other assumptions, no oblique assumption or anything. Another way to say it is, as we'll see in a second, this is already sensitive to these operators at the scale of a few TeV. But in order for example, the denominator to be modified, the scale of the operator, since this is a tree-level coupling, would have to be way down at the couple hundred GeV scale. So if all the operators are uniformly up at the few TeV scale, then it's just these 3. Okay? And that goes even, for example, for the top coupling. You might say, well, the top coupling, it's going to get some effective operator that would modify it. But again, if it's up at the TeV scale, parametrically, it's a loop suppressed compared to these operators that contribute directly to the diphoton. So now let me just draw the pictures here. So these three operators will always be the best of the 50, just numerically, another way to say it is, by a factor of about 100 than any of the other operators. So they're special in that sense. So now okay, so before we had to live in this band and there was no information about this. So now it's some ellipse that's a little bit more squashed in this direction. So it turns out the linear combination is the combination along the diagonal. It's being bounded. And so just right at the discovery level, this ratio has already bounded these other operators morally at basically the same scale as the S operator. And in the future, this will shrink down quite a bit. So a 5% measurement's a tiny little, smaller than that. It's like a factor of 10 almost in the aspect ratio of the ellipse. Okay. So Higgs to dibosons are this will be the new precision electroweak physics. So that's one impact these rate measurements will have. And in general, how to handle these 50 operators or organize it in different ways to pick with some motivation about which operators are important, which aren't, and so forth. So that's people haven't worked all that out. And I want to just make one comment about the linear collider, electron-positron linear collider. Basically, almost anything about the Higgs boson can be measured better, probably, at the linear collider than at the hadron, at the LHC, just because it's a much cleaner environment. It's easier to make precision measurements, except for this. This will always be best measured at the LHC. And the reason is the ILC never produces that many Higgs bosons. In fact, we've already produced more Higgs bosons than the ILC will probably ever produce. It's just that we didn't even record most of them, right? But this is a rare branching ratio. Okay? So you need the high number of Higgs bosons to probe this particular final state. So the diphoton final state will never be probed so well. And this particular ratio, I think, in the end, of course, it has to be studied exactly what the systematics will be, I think could easily approach the percent level eventually. Okay. Next subject I want to talk about now for Higgs decays, and what they'll be interesting for is non-standard model decay modes of the Higgs. So this is an interesting subject. And the idea is, well, the reason that the Higgs is an interesting system in this sense to decay to light things is that this dominant decay of Higgs to BB, remember that's coming through a very tiny coupling. So if there's any extra sector, like some kind of dark sector that Nima mentioned yesterday, that's light, a bit below the electroweak scale, if it couples to the Higgs even a little bit, since this coupling is so tiny, it's 10 to the minus 2, well, the Higgs has a pretty good chance then to couple into that sector. And maybe we could see it. So it's just one example. Well, I'll give a couple examples. Let's see, will I? Yeah, I'll give two examples. So one, in a 2 Higgs doublet model, so many ideas for extensions of the standard model introduce an extra Higgs field. So the minimal supersymmetric standard model has 2 Higgs fields, as I'm sure you'll hear about later in the school. So I'll just call them Higgs 1 and Higgs 2. So let's just look at the particle content. So one linear combination of these, all the degrees of freedom are already accounted for. So each of these has 4 degrees of freedom. So 3 of them become the extra polarization states for the W and Z. One of them is the Higgs, so there's one full SU2 doublet worth left over of degrees of freedom of particles. And so those are, aside from the Goldstones, there's the H. There's one more field that has the quantum numbers of the vacuum. So the extra fields are just the ones that say, live in the second Higgs. There's a pseudoscalar that's odd under parity and time reversal, and there's a charged Higgs boson. So these are the guys that would have been the Goldstone bosons if there had only been one Higgs. But in the second Higgs, then they're actual real particles, because they're not eaten. Only one linear combination is eaten. Now, if the potential, if this extra Higgs sector has an approximate symmetry, a global U1 symmetry, under which this pseudoscalar transforms inhomogeneously, then the pseudoscalar could be much lighter than the other fields. And that's technically natural. So we had these nice discussions of technical naturalness yesterday. So this is an example of technical naturalness because there are some parameters that would, in particular, give a mass to this field, A, that if we set those parameters to 0, we regain a symmetry, a U1 symmetry. So an example is a Peccei-Quinn symmetry. Where the H1 and H2 fields have, say, charge plus and minus, if they have the same hypercharge. Okay. And so you regain a symmetry as you set the interactions that violate that symmetry to 0. So if you set them to 0, there would be at tree level a massless Goldstone boson if both fields have an expectation value. And it's technically natural that that breaking of that symmetry that lifts this could be small. So that's just a long-winded way of saying that it's technically natural to have this one field lighter than all the rest of them. But now if you inspect the general couplings, even in this limit, you can have couplings of the Higgs field to this light A field. But now in the light A field, so to two A's, and again, this coupling here would naturally be suppressed by the mass of the A, so it's tiny, but it's only fighting against the coupling that's, for importance, that's already small anyway. So it could be a sizable branching ratio of the Higgs boson. It could be 10%, 5%, a few percent. And now the A, since it's coupled, it's some linear combination of these Higgses, and some of the Higgses have to couple to the fermions, it can decay to fermions. And so just like the Higgs, it'll decay to the heaviest fermion it can. So experimentally, a good thing to look for, or the easiest thing to look for, is when this decays to dimuon pairs. So one looks for events where, it's not so likely to construct all 4 muons, but in particular, if you did, the 4 muons in pairs would make a mass, a new mass that you would discover, and altogether they would make the Higgs mass. So this is a process that's being searched for, and there are other things like this, looking for non-standard decay modes of the Higgs boson. Another one that I want to talk about is Higgs decay to dark matter. So if there's WIMP dark matter, again, you're going to hear a nice couple lectures from Neil Weiner next week about dark matter and connections with LHC. So I just wanted to say something about that. Well, if the dark matter happens to be lighter than half the Higgs mass, then this is an open decay mode. And it could be looked for directly. Let me skip that in the interest of time and talk about the indirect couplings. Well, how would the Higgs couple to the dark matter? Well, we can use the soft Higgs theorem again to calculate the coupling. So the coupling, by definition, is determined by how much the dark matter mass depends on electroweak symmetry breaking. So in general, you would expect, let's see, so if we define this to be some constant, now, it almost certainly does not get all its mass from electroweak symmetry breaking, because then if it was that light, it would have gauge quantum numbers and we would know about it. Okay? So this F here, but I can parameterize it this way. So F was 1 for the standard model fields. F is less than 1. And, well, just on general grounds, if it's a weakly interacting particle that arose from freeze-out and it has a mass, just below the weak scale, it has to couple to the Higgs at some level. So this F is not 0 at some level. Okay? So if there is a light dark matter particle, the Higgs will decay to it at some level. The only question is how big is this F, and therefore how big the branching ratio is. So if we look at the effective Lagrangian in the dark sector, so if we imagine a fermion, a Majorana fermion, so there's the Majorana fermion, like neutralino dark matter, that has some mass term that's not directly coupled to electroweak symmetry breaking, but in the effective theory, as long as these things couple somehow, at some level, effective operator of this form, a dimension 5 operator will be generated. And then when the Higgs gets an expectation value, that'll contribute a little bit to the mass of the dark matter particle. Okay, so again, it will couple. And for example, this is a limit of the MSSM. You obtain this. So in the MSSM, with the BINO, the partner of the hypercharge gauge boson, much lighter than the Higgsinos, then, and this is a dark matter candidate, then the BINO, there's effective, this operator is generated. And the BINO gets some of its mass, say most of it from supersymmetry breaking, but through these interactions in the low energy theory, it gets some mass from electroweak symmetry breaking. So if it were light enough, the Higgs would decay to BINO pairs. And if the BINO were dark matter, it would be decaying to dark matter. Now, from these rate measurements that I discussed before, there is enough information now actually to get a bound already on the branching ratio of Higgs to any non-standard model state. And the reason is because there's already evidence for all the important decay modes, the BB, the couplings to gluons, W's and Z's, and tops. Okay? By the way, if there weren't any evidence for any coupling to B, there would be a degeneracy. In other words, you could imagine you could send the B, you could make the B small, and then increase this non-standard model branching ratio at the same time, and then you say, okay, I had no idea. But even now, there's some evidence. The evidence favors a non-zero coupling to the B through the searches looking for Higgs to BB in association with a W, leptonic W, that again you'll hear about later. And so there's already a bound on this non-standard model branching ratio, which is kind of interesting. And that'll only get better as time goes on. So in particular, the Higgs to invisible is bounded by this. So the bound's about 60% right now. So that gives us a bound here if we had a light dark matter particle on how strongly it couples to electroweak symmetry breaking. And so just to take an example, if we have 10 GeV, so if m chi is about 10 GeV, well, 10 GeV is not so far from the B mass. And so even before we plug in any numbers, we see that this F will be bounded. It's a number of order 1. So when you plug in the numbers, F has to be less than about 0.6 from this number. Let's see if I remembered it right. I wrote it down somewhere. I can't find it, but I think that's the right answer. It's a number, it's of order 50% or so. Well, that's not a really stringent bound yet, but we can use that to make a relationship immediately with direct detection of dark matter in the laboratory. So let me just sketch how that goes. And I'm almost out of time. I'll just take another few minutes. Now, the direct detection for dark matter, for WIMP dark matter, uses nuclear recoil. So the idea is that there's some short-range interaction between a dark matter particle and a nucleon. And since there's tons of if there's WIMP dark matter, there's about one per, well, it depends what the mass of the particle is. It's about one per, a little bit less than one per this volume here. And they're flying through the room at about 300 kilometers per second. So there's a huge wind of WIMP, and you can't there's too many of them. You can't avoid them. They're hitting you all the time. Not very often, but if you make a precise enough detector to try to look for the nuclear, so the WIMP comes in, it scatters off a nucleus, and you can look for this recoil of a single nucleus. So that's how the direct detection works. But you see, now there's something interesting here. Again, we argued that if there is WIMP dark matter, it's going to couple to the Higgs no matter what. If it's light enough, the Higgs will decay to it, and we already got a bound on that possibility. So these interactions here will come from interactions like this, and they basically have to be there at some level through the Higgs. And the Higgs, as we discussed earlier in the lecture, couples to gluons, and the gluons have some expectation value inside the nucleus. So we can make a relation between this bound we get on the decay, on how strongly the Higgs can couple to the dark matter, and just turn that around and use that to give us a constraint on how big the direct detection could be. Now, I'm not going to do it. You can ask me about it in the discussion section. I'm out of time. But you can use the low-energy Higgs theorem to calculate in a certain limit, exactly to leading order. Well, you can calculate very well what the coupling of the Higgs is to the nucleon through these gluon fields. So you might think, well, you just have to estimate the matrix element. But using the soft Higgs theorem, you can get the correct answer reliably with only perturbative correction. So that's sort of an interesting application of the low-energy Higgs theorem, but I've run out of time, so I won't be able to discuss that in detail. But I can show you that privately if you want to see it. And so that tells us, basically, there's also an F for the nucleon, and basically we can calculate F for the nucleon pretty well, in the limit that the light quarks were massless, actually. Okay, so when we do that, so I'll just write the answer. It's about 0.22. If the light quarks were massless, they're not massless, so this gets corrected. And now, okay, so now, all right, I went to all this trouble about saying how well we could how clever we are, we can calculate it, but actually the light quarks ruin it, and so the estimate's somewhere between 0.3 and 0.5. But all right, anyway. Okay, with this uncertainty, one can calculate the cross-section for scattering of a dark matter particle off a nucleon. And so here I did it, so I'm going to write it down. F nucleon squared. And this is through the Higgs, T-channel Higgs exchange, M nucleon. Okay, there it is. And with only a moderate uncertainty in this F nucleon, and then a bound, again, if it's light enough, the Higgs decay to it, a bound on F from the Higgs decay. Right? So we can attack this problem from two sides, from the direct detection side and from the LHC side. Now, picking this number of 10 GeV, just as a reference number, one finds then from the invisible width bound, the cross-section, when you plug the numbers in, has to be less than about 9 times 10 to the minus 46. This is per nucleon, square centimeters. So that's interesting. So that says that a 10 GeV dark matter particle, well, neglecting any other interactions that might happen or cancellations, will have a direct detection cross-section smaller than this, at least through this Higgs interaction. Now, as most of you probably know, CDMS, and Neil, I'm sure, will talk about this in some detail, saw 3 events that could be consistent with a light dark matter particle in this mass range. And they see and the implied cross section for these three events would be about 2 times 10 to the minus 41 square centimeters. So immediately from the LHC, we see that, well, if that's true, it is not interacting through the Higgs field. Because if it did, it would have completely destroyed the width of the Higgs. The Higgs would have been decaying mostly to this invisible thing. Okay? So we learned that if you want to believe these things, they do not couple. The interactions, these interactions here are not mediated by the Higgs. Okay? So that's an example of another way that the dark matter connection with the Higgs decays. Okay, I think I'll stop here and just tell you the other topics that I had planned to talk about and just what the results are. Another is coming back to these effective operators in classes of theories that try to address the hierarchy problem, the quadratic sensitivity of the Higgs mass operator to high scales. You often have partner particles. So in supersymmetry, you have partner particles that cancel the quadratic divergences because the partner particles have opposite statistics, so they have opposite zero-point energy. They have minus a half h bar omega, not plus a half h bar omega. And so in the very low energy theory with just a standard model, there's this apparent quadratic sensitivity, but then once you get to the effective theory with the superpartners, then that's gone. Now that's interesting because those partner particles have to couple to the Higgs by definition if they're going to reduce the if they're going to eliminate the quadratic divergence. In the simplest case, they should have the same gauge quantum numbers as the top quark, although maybe that's not really necessary at one loop, but if you wanted a full solution like supersymmetry that sort of worked at all orders, I don't know how you'd avoid that. Oops. So they couple to the Higgs, and they couple to strong interactions, and so they'll modify this Higgs to glue-glue interaction. So it's just an irreducible consequence of having partner particles that the Higgs to glue-glue and also the Higgs to diphoton, with some maybe just tiny exceptions, are modified. Okay? So if there's a solution to the electroweak hierarchy problem that involves partner particles, there will be deviations in these couplings at some level. That's just essentially irreducible. Okay? So that's an interesting statement. But when you look at it numerically, and again, we can use our soft Higgs theorem again to estimate how big these are, and it turns out that they could be as small. Well, it depends where they are, and the problem is that the partner particles in almost all theories get mass, some from electroweak symmetry breaking, so they couple to the Higgs, but they also get mass from other effects, like in the case of supersymmetry, that get mass from supersymmetry breaking. And that dilutes the coupling here to the partner particles. So you don't have this nice effect anymore. Remember, for the top quark mass dropped out. But now if these extra partner particles get mass from something else, that doesn't happen anymore, and it suppresses the effect. So it could be, even if there are say stops there at 500, 600, 700 GeV, these modifications might only be at the percent level. And that's much smaller than anybody's ever discussed for getting theoretical control over just the standard model calculation of that and the PDF uncertainties. So unfortunately, although of this paradigm that we talk about, there is a definitive prediction. It's not definitive in magnitude, only qualitatively. It's there, but we don't know how big it is, and it might be too small. And for the photon, that might be a little bit better, because then we can go to these ratios and so forth. But there, it's dominated by the W boson loop. And that gives such a big contribution that tends to suppress it too. So that might only be at the percent level or less. Although long term, maybe that would be, from these branching ratio measurements, that would be a possibility. Okay, final thing that I'll just say to end, and I won't give any details, is that the last, a final way that we're going to use the Higgs is being used already, is to look for new physics. And there's a saying in experimental physics, high energy physics, particle physics, that yesterday's discovery is today's background and tomorrow's calibration. Okay? So once you find a new particle, then, well, once you know its properties, you can use it then to search for other things. So that was done with the W and the Z boson and the top quark, and now the Higgs. In fact, I think the Higgs, it was the first particle where it went directly from, before discovery, we were already worried about it as backgrounds, polluting some of the multi-lepton searches, perhaps, that you're going to hear about from Sunil next week. And even when there was just a hint, we already started the first use of it as calibration. In particular, one question came up, well, okay, suppose it's there in this little bump that maybe is there in the diphoton spectrum, or no, we don't know. Okay, so suppose it's the Higgs, but maybe 30% of that is coming from some new physics. So even before it was established that it was an actual literal discovery, you could just go, it was possible to go look at the data and say, just suppose you look at that data, is it consistent with it being a standard model Higgs, or is there some other blazing thing there? It could have been stop squarks that were spitting out, being pair produced and decaying to Higgses and so forth. And so I think the Higgs skipped directly from pre-discovery to calibration. And there's a number of ways, so I'm out of time, I'll stop. But there are a number of ways now that are actively being pursued that are using the Higgs as calibration to look for new physics. So this can happen in supersymmetry. So one way is a stop squark can decay to a lighter stop squark emitting a Higgs. A neutralino can decay to another neutralino emitting a Higgs. And so it's under active experimental investigation now, looking for those signatures, given that we know the properties of the Higgs. So that's another exciting possibility of using the Higgs now that we have it in hand. So I'll just finish by saying, repeating what I said in the first lecture in the beginning, it's exciting times. As you see, things are in flux experimentally. Not everything has been figured out, even what can be done cleverly on the experimental side. There have been lots of ideas on the theory side. And if we find anything in the data at the LHC, I think it's very likely that it will really crystallize the way we think about things and point in a certain direction. So you're lucky to be in the field when your minds are young and nimble and not, old and not nimble. And you don't have all the prejudices built in. So I hope somebody here figures out how to find new things in the LHC data and then once it's found, figures out what it means. Okay, that's it.